welcome to the deep dive. Today we're tackling a topic that literally holds everything together, elasticity.
It sounds straightforward, doesn't it? Things bend, things stretch.
Right, but underneath that is this, incredible mathematical framework. It's behind bridges, buildings.
Even how earthquakes travel. Absolutely. And we're diving into the source itself. Chapter 38 of the Feynman Lectures on Physics, Vol.2.
Classic.
It really is. Our goal today is to sort of decode how materials respond. We need to get into these fundamental constants that describe how solids react to pushes, pulls, twists.
And see how that microscopic stuff leads to, well, big picture things like beams bending or columns suddenly buckling.
Exactly. Elasticity is that connection, that bridge between the tiny forces holding atoms together and the large-scale mechanics keeping structures sound.
So we'll define these key numbers, like Young's modulus. Look at how waves move through solids, which is kind of surprising. And figure out why, sometimes, the length of a beam matters way more than what it's made of.
So we'll start with the basics, move beyond just force and stretch to the material properties themselves. Then we'll look at different kinds of deformation, connect that to waves, and finish up with structural failure, how things break.
Okay, let's start at square one. Hooke's law. The simple idea, right? You pull something, the force is proportional to the stretch.
Double the force, double the stretch. We all learned that.
But crucially, only if it snaps back. Only in that elastic zone.
Precisely. Because if you just measure the total force and the total stretch, that only tells you about that specific wire or that specific spring.
Right. A thick steel cable and a thin steel wire won't stretch the same amount under the same weight, even though they're the same material.
Exactly. To talk about the steel itself, we need something more fundamental. We need intrinsic properties.
So we shift from the object to the material. That's where stress and strain come in.
Yes. We normalize things. Strain isn't just the stretch. It's the stretch divided by the original length. A fractional change.
Ah, so it's a ratio. Doesn't matter if it was initially long or short?
Correct. And stress isn't just the force. It's the force divided by the area it's acting on. The force per unit area.
Okay, so we have intensity of deformation, strain, and intensity of force, stress, and the link between them.
That's our first big constant, Young's modulus. We call it dollars.
So this dollars is the material's inherent stiffness.
That's it. High dollars for steel means it's hard to stretch. Low dollar for, say, rubber means it stretches easily. It's a property of the material.
Okay, makes sense. But then things get a little less intuitive. If I pull on something like a block, it gets longer. But doesn't it also get thinner? Sideways?
It does. It contracts laterally. And that effect is captured by our second key constant, Poisson's ratio, usually written as sigma.
Sigma. So this tells us how much it shrinks sideways compared to how much it stretches lengthwise.
Exactly. It's the ratio of the fractional sideways contraction to the fractional longitudinal extension.
Is it usually a big number or a small number?
Generally small and positive. For most materials you encounter, it's somewhere between 0 and 1/2.
0.5. Why that specific limit?
Ah, well that ties into what happens if you squeeze something from all sides. If sigma was exactly 1/2, stretching it wouldn't change its total volume at all. The sideways shrink would perfectly balance the lengthwise stretch. Anything higher than 1/2 leads to some physically weird, unstable situations, which actually brings us nicely to the next idea, uniform stress.
Okay, so instead of just pulling, imagine taking our block and dunking it deep in the ocean. Pressure pushing in equally on every single face.
Right. Uniform hydrostatic pressure, what happens to the volume?
It must shrink, right? Get smaller overall.
It does. And you can actually work out how much the volume changes using the constants we just defined, Young's modulus dollar and Poisson's ratio, sigma beta.
Ah, so they're connected.
They are. The relationship between the pressure applied and the fractional change in volume, delta VV, is defined by the bulk modulus. Let's call it dollar.
So dollars is resistance to being squeezed uniformly. And it depends on both dollar and sigma, huh?
Yes, it does. You need to know both how stiff it is, why, and how much it bulges or shrinks sideways to know how it responds to uniform pressure.
And this connects back to that limit on sigma.
It does. The formula for dollar involves $1 sigma in the denominator. If sigma dollars were greater than 1/2, $2 would become negative, meaning
it would expand when you squeeze it, which is impossible.
Exactly. So the math confirms sigma dollars can't be bigger than 1/2 for stable materials. It's a neat little consistency check, Feynman points out.
Very cool. Okay, we've done stretching, we've done squeezing. What's the third way?
Shear. This isn't pushing or pulling directly. It's like sliding layers past each other.
Like pushing the top cover of a book sideways while the bottom stays put.
Perfect analogy. The book distorts, right, into a sort of parallelogram shape.
Yeah, it skews.
That angle of skewing, that's the shear strain.
Yeah.
And the tangential force per unit area causing it, that's the shear stress.
Okay, strain is the deformation, stress is the force intensity, so it must be a modulus for shear too.
There is. The shear modulus, often called mu-daw, sometimes called the coefficient of rigidity. It measures how much a material resists this shearing, this sliding deformation.
So we have dollars for stretching,
Like
dollars for bulk compression, and U-dollars for shear. Are these all separate independent properties?
That's the fascinating part. No, they're not independent. They are all linked through Poisson's ratio, sigma dollar. If you know any two of them, say U dollar sigma, you can actually calculate the third one. Wow.
So the way a material stretches and squishes sideways actually dictates how rigid it is against shear.
Fundamentally, yes, it all interconnects.
All right, we've handled static forces. Let's get things moving. What about twisting? Like wringing out a towel, but maybe a solid rod. Torsion.
Good example. When you twist a cylindrical rod, the material experiences shear stress. The further out from the center axis, the more shear it feels.
Okay, so the total effort needed to twist it, the torque, must depend on how much you twist it, and the material's shear resistance.
It does. It depends on the twist angle per unit length and on O dollars. But here's the kicker, the really surprising part from the derivation.
What's that?
The total torque is proportional to yes, but also to the radius of the rod raised to the fourth power.
The fourth power.
Seriously.
Seriously, think what that means. Double the diameter of a solid rod.
And its resistance to twisting goes up by 2 times 2 times 2 times 2. 16 times.
16 times stiffer against twisting. That's why hollow tubes are often used where torsional strength is needed. You get most of the stiffness by having material far from the center, but save weight. That 443 is hugely important structurally.
Mind blown. Okay, and that twisting doesn't just happen instantly along the whole rod, right? It travels.
Exactly. A change in twist propagates down the rod as a wave. A shear wave or a torsional wave.
So our elasticity constants now connect to wave speed.
Directly. The speed of this shear wave depends on the square root of the shear modulus muth divided by the material's density. Square root of over also. Okay. But solids can also carry regular compression waves, right?
Right.
Like sound waves, longitudinal waves.
They can. P waves, primary waves, like in earthquakes.
How do their speeds compare? The shear wave versus the compression wave.
Well, because of those relationships between nu and sigma, the shear modulus mood is always less than the combination of constants that determines the longitudinal wave speed. Always.
Which means?
Shear waves always travel slower than longitudinal waves in the same solid material.
And that's huge for seismology, isn't it?
Absolutely fundamental.
Yeah.
An earthquake sends out both types of waves. The faster longitudinal waves, P waves, arrive at a seismograph first. Then, sometime later, the slower shear waves, S waves, arise.
And the time gap between them tells you
how far away the earthquake happened. By comparing arrival times at different stations, you can pinpoint the epicenter. It relies entirely on that speed difference, which comes straight from the elastic constants.
Amazing. Okay, let's shift gears again to maybe the most common structural issue. The bent beam. Think about a shelf sagging.
Right. When a beam bends downwards in an arc, picture it. The top surface is getting compressed, squashed together.
And the bottom surface is getting stretched out longer.
Exactly. Compression on the inside of the curve, tension on the outside, so the stress isn't uniform across the beam's thickness.
Which implies there must be a layer somewhere in the middle that's neither compressed nor stretched.
Precisely. That's called the neutral surface. And the strain, the amount of stretch or compression, increases the farther away you get from that neutral surface towards the top or bottom.
Okay, so the beam is internally fighting this bending. How do we quantify that resistance?
That resistance is called the bending moment, math-rec. It's like an internal torque that counteracts the curvature. This moment is proportional to how much it's curved. 1 over the radius of curvature, Longo's dollars, Young's modulus dollar, and another crucial factor.
Not just the material, but the shape.
Exactly. It depends on a geometric property of the cross-section called the moment of inertia, A dollar.
Moment of inertia, all dollar. That sounds familiar from mechanics, but different here.
Sort of. It's calculated by integrating the square of the distance from the neutral surface over the whole cross-sectional area. Y-day-S ain't Y2 DAO. What it means is how effectively the material's area is distributed far from that neutral surface.
Ah, so that's why I-beams are shaped like an eye? Most of the metal is in the top and bottom flanges, far away from the middle.
Precisely. That gives a huge moment of inertia, all dollars for the amount of material used, making it very resistant to bending. The shape is often much more important than slight differences in the material's dollar.
Okay, let's use this. Say a diving board, fixed at one end, someone stands on the other. A cantilever beam. How much does the end dip down?
You can calculate that deflection using the bending moment relationship.
Hmm.
The deflection at the end turns out to be proportional to the weight on the end, and here's another crucial dependent.
Length must be involved.
It's proportional to the length of the beam cubed, 3 ohm through 3 ladders.
Cubed. Whoa.
Yeah, so if you make a cantilevered beam twice as long, keeping everything else the same, it doesn't just sag twice as much, it sags 8 times as much. 2 cubed.
That's a massive penalty for length. Engineers must really fight that 303.
Constantly. Managing deflection is often about managing that cubic dependence on length.
Okay, one last major topic from the chapter.
Hmm.
The really dramatic failure. Buckling.
Ah, yes, buckling.
Hmm.
This isn't about the material breaking strength, usually. It's about stability. Imagine a long, thin column, like a ruler stood on its end, and you push down perfectly straight on the top.
Okay.
If you push hard enough, even if the material isn't close to its crushing strength, the column will suddenly just bend sideways. It becomes unstable and collapses.
It just gives way. That's buckling.
That's buckling. It happens when the compressive force you apply exceeds a critical value called the Euler force.
And what determines that critical force? Is it length again?
Oh, absolutely. The critical buckling force is proportional to Young's modulus dollars in the moment of inertia, just like bending stiffness.
Yeah.
But it's inversely proportional to the length of the column squared, to a lat$2 too.
Inversely proportional to length squared. So longer columns buckle much more easily.
Vastly more easily. Double the length, and the force needed to buckle it drops by a factor of 4. This isn't about the material failing, it's about the geometry becoming unstable under load. Absolutely vital for designing columns in buildings or supports in rockets.
Wow. Okay, so recapping this whole journey through elasticity.
We've really gone from the microscopic material constants, illinolar, new dollars that tell you how a material fundamentally responds,
The inherent properties.
all the way up to these large-scale behaviors like bending and buckling, where the geometry, especially the length, plays these huge, often exponential roles. 303 dollars for bending deflection, 200 for buckling instability.
So for you listening, the big takeaway isn't just use strong materials. It's often about smart design.
It really is. Understanding how shape, through things like the moment of inertia or dollars, and how length's dependencies dictate performance. An I-beam isn't just strong steel, it's cleverly arranged steel.
And maybe a final thought to leave you with, tying back to those waves. We learned that seismologists use the time lag between the fast P waves and the slower S waves, shear waves, to find earthquakes. Now think about this. Shear waves require rigidity. They need that shear modulus bends. Pure liquids have zero rigidity. Mu equals a ladder. What does it tell seismologists about the deep structure of the Earth when they observe regions where S waves just disappear, where they don't propagate through?
A very deep question indeed. Something to ponder about the Earth's core, perhaps.
Absolutely. Well, thank you for joining us on this deep dive into the physics of elasticity, drawn from Feynman's insights.
A pleasure. Thank you for sharing your sources with us.